Okay, so it's time to get started. Um, Hello, everyone. My name is Savannah. I will be a tutor for Chemistry 221 for this term. And for myself personally, I'm a mechanical engineering student, and I really enjoy chemistry. And I really like teaching a lot of the fundamental concepts I always have. And yeah, so we'll get started on to this week's material. We will be talking about significant figures as well as unit conversions. So let's get started. This will be on chapter 1, end of chapter questions. So I will write down specifically what questions I'm going over. And if you guys want the link to the chemistry textbook online, I can put that in the chat if you'd like that. So let's start it. So we'll be going over significant figures. Significant figures are very important as oh, hello, my new viewer. But we're just getting started on significant figures, and they're very important in research, especially as well as just your everyday calculations in your professional career. You know, if you're an astrophysicist and you're calculating the meteor around Earth, you know, it's very important exactly how far away it is, and that's an extreme example, but it goes to show how important significant figures can be. And then later on, we'll get into unit conversions, and that is also very, very important in your careers. And if you know, you're just calculating milliliters, liters, and whatnot. So we'll get started on significant figures. So 44A is the first question that we'll answer. And we have the value of 711.0. So when we go about significant figures, it's important to note when the non-zero values start and if they're decimal place. So we have non-zero values here before the decimal place, and we have a period as well as a zero after it. And because there is this decimal place here, we include all of the values after it because there are also non-zero values here. So this has change the size, 1, 2, 3, 4 values. So this has 4 significant figures. Okay, let's get on to the next question. So this is 44B, and it's 0.239. And so because there are no non-zero values before the decimal place, we do not include this. So we only include it once the non-zero values start after the decimal place. So because of that fact, we have 1, 2, 3 significant figures here. So we have 3 sig figs. Now on to C. Let me know if I'm going too fast or if you need any more explanation on anything I'm going over. So for this value, we have 90,743. And so because there are no decimal places, that doesn't really take into any factor here because we have all non-zero values, or most of them are non-zero values up until the last in the one place. And so because of that, we include each and every one of these values because it ends in a non-zero value. If, for example, this was 90,740, we would have 4 significant figures. But because there's a 3 here in the ones place, now this question has 5 significant figures. Okay. For that basis, we know the sig for all of these values. Let's look at how these will look like in scientific notation, because we want to keep the amount of sig figs here, but we also want to, if we want to reduce it to a smaller value, timesing by 10 to whatnot, it's important to know how many sig figs we're keeping track of. So for the scientific notation for these, 711 for 4A would be 7.110 times 10 to 2. And the reason why we do this is because for scientific notation, we want a value between 1 and 10. And when we want to reduce to that value, we want to multiply it, obviously, by whatever factor we need to get it up what it was before. So, for example, since we have 711 here, it moved 1, 2 decimal places. We moved back. And so since we have 7.110 now, to get it back up to 711, we multiply it by 100. And in scientific notation, that's 10 to the second power. So now to 4b. So because we have a 0.239 value, we need to bring it up to a value between 1 and 10 for the first term. So we will have 2.39, and because we moved it 1 in front, we want to multiply it by 10 to the negative 1 because we moved back 1. So we want to reduce it. Okay, so for next one, we have 90,743, and so because of that factor, we have to reduce it to 9.0740. So in order to do that, let's first write down the first term. And since we transferred to 90,000 to 9, let's see how many decimal places we moved back. So that would be 1, 2, 3, 4. And so because of that basis, we times it by 10 to the 4. It's also important to know if you're going from a larger to a smaller number, because that matters if your 10 to the exponent is positive or negative. Because in example B, we have 0.239 and we brought it up, and we need to bring it down when we're multiplying by 10 to factor. So that's why it's by times 10 to the negative 1. Okay, let's move on to more significant figures. And we're going to go over 48A. And so this value is 38.7 grams. So we want to see how many significant figures this is. And similar to what we already established, there are all non-zero values here. That's going to be 3 significant figures. And we want to include all, especially because there's a decimal place. So because of that basis, then this is the significant figures. Let's go on to 48b. 48b is 2 times 10 to the 18th power. And so because there is only a 2 here, whenever there's a scientific notation, we always do not include how many significant figures there are when there's times 10 to what a power, because this is how scientific notation is, because we're basing it off of this value here, because we want to lower it or higher it, whatever it was before. So this is the value we're very concerned with. So because it's just a 2 and there's only one of them, we have one significant figure here. Go to 48C. So 48C, we have the value of 3,486,002 kilograms. And so because there is a non-zero in the ones place here, we include everything else beforehand. So because of that basis, we have 1, 2, 3, 4, 5, 6, 7, 6 figs. Okay. And for E, I want to go over a problem that has a decimal place as well as a 0 after the decimal place, and whether or not we include that or not. So for that value to represent that example, we have 0.0613 centimeters cubed. So because we have a decimal place here, we need to try to figure out what place we will need to start counting the significant figures. So because there's a decimal place and then there's a 0 here, we do not include the 0, because we include most of the time, whenever the non-zero values start, that's usually when we begin to start adding significant figures. And because of that basis, then we have 3 sig figs here. As you can see, over all of these, it's whenever the non-zero values start and when they end. So if there's a decimal place, we always include whatever was before. So if we have 4,000 and then a decimal place, such as this, with a decimal right after it, then we're going to include all of these significant figures because of this decimal place here. So this, for example, would have 4 sigs. So it's very important when, let's just say you have a problem on exam and it says, you need to use 4 significant figures, but you only have a 4,000. And traditionally, if you didn't have a period right there, it would only have 1 significant figure. So using that decimal place is really important because it gives value to all of the values before it. Okay, let's move on to 52A. So we're going to be rounding these values to whatever significant or whatever place the question asks of us. So for 517, it asks for 2 significant figures. And so when we're rounding this, we want to include these 2 places right here. And because the value right after it is 5 or more, then we round the 1 to a 2. So that would look like 5, and we keep the 5, and then we round it to 520 because the 7 is 5 or more. So let's go to B. We have the value of 86.3, and we also want to round it to 2 significant figures. So that will look like 86, and we'll keep it at that. We can put a decimal place right after it or not because the 6 is a non-zero, so it's not important to put the decimal place. If, for example, this was 80.2 and we wanted to have 2 significant figures, we would want to do 80 period because it includes this 0 and therefore it would have 2 significant figures. But for 86.3, we can keep it at 86 because this 3 is 4 and under. So we do not round up to 87, for example. Okay, let's move on to 52C. So we have 6.382 times 10 to the third. And we want to round to 2 significant figures. So we want to keep the 6, so we only have 1 so far. And we're looking to have a value right here. So because the 8 is 5 more, we round up. So that would be 6.4. So that'd be our value for that, and then we keep the 10 to the third power. Because, if we did not have that, that wouldn't be the same value at all. It would be 1,000 times less. Okay, let's move on to 54A. And these are calculating with significant figures. That becomes a lot more tricky, and it's always something I've struggled on because you really need to keep track of how many significant figures you're multiplying and dividing with, as well as we'll get on to the next example as adding and subtracting. So with multiplying significant figures, you want to use the least amount of significant figure that you've used so far. So that looks like for 54A, we have 62.8 times 34. And so because the first value has 3 terms here, and then this one has 2, significant figures, we will use 2 significant figures because that's the value that we're most certain on. So we will only have 2 significant figures in our answer. So 62.8 times 34. Let me just multiply that really quickly. That is 2,135.2. so since we only need 2 significant figures, hello everyone who's recently joined, this will be 2100. Let me know if you want me to go over more significant figures or scientific notation, people who just joined. I can easily go over that again. And so because, like I said, when multiplying, you keep the least amount of significant figures you are multiplying. And that as well goes for dividing. So multiplying and dividing whatever least amount, that's what you use for your answer. Okay, so 50 for B, we have an addition problem. So when adding significant figures, it becomes very tricky as well. So you have 0.147 plus 0.0066 plus 0.012. So this one is tricky, and I've always kind of struggled with keeping track of these. So what I do to prevent myself from messing up, I always stack them and to kind of see where their decimal places are. So you want to round to whatever least decimal place or the highest decimal place that every value is certain in, if that makes sense. So I'll explain what that looks like. So we have this value, it's the longest, so I'm going to write that down first, and then these two are 0.12 and then 0.147. And we're adding all these. And so because when we stack them like this, we have all of the values lined up right here, that means we're all certain in that ballpark. And so because of the factor, then we're going to round to that place because we're certain in all of those areas. Hello to everyone who just joined. So adding that, I'll do it the old-fashioned way, I guess. So it's 6, and then we have 8, 7 is 15, 31, 6, 1, 0, 1. So this is the value that we have, and because we need to round to this place, our final answer will be 0.16 because we're certain in that value place. Okay, let's move on to unit conversions. Unit conversions are so important. You'll use them all the time, whether you're an engineer like myself, or you're going into chemistry or research, or you're going to be a doctor or a nurse, whatnot, or a pharmacist. You use unit conversions all the time, and they're so important. So let's start with our first problem. It is question 66. So it describes the distance of 2 oxygen atoms in an oxygen, that a little bit, oxygen molecule. And so the distance between these atoms is 1.21 times 10 to the negative 8 centimeters. So the question asks us to put it into inches. And so what I always do with canceling out units and get kind of messy. So what I like to do is do 1.21. Let's start with our value, just 10 to the 8 centimeters. And our goal is to get to inches. So I always put this value under 1 because it makes it easy for canceling out units to avoid getting confused with which one am I canceling out. Because if you just kept it, this for example, and then we'll use this factor, there's 2.54 inches in 1 centimeter. It can get kind of confusing because you see both of these centimeters and you don't want to cross out because they look like they're adjacent to one another, but they're not. So I'm going to be using this example here because it's easy for kind of keeping track of that. So using the same value from centimeters, inches, in 1 centimeter, there is 2.54 inches. And so because now we see it's so easy to cancel out these units because we obviously know that these two are on top and on bottom, so they cancel out one another. So we're left with inches. Sorry, I probably should have swapped the green and the red. But so because of that basis, now we can multiply, not cross multiply, multiply directly these two values. So 1.21 times 10 to the negative 8 times 0.54 is 3.0734 times 10 to the negative 8. And so now what we have already established before is significant figures. So because this value right here, the 1.21 times 10 to the negative 8, significant figures in this value is 1, 2, 3. There's 3 significant figures, and we do not include the 10 to the negative 8 for scientific notation, because it's just multiplying whatever the true number value what we have, and we have 1.21. And so because we have 1.21, 3 significant figures, now we will round our final answer to 3.07 times 10 to the negative 8 inches. Okay, so now we kind of understand how to do some unit conversions. Now let's get into some more of those. So I'll leave this up here if you are writing this down. So here's 72A. And so we want to transfer grams to, or convert grams to milligrams. So I always like to know my fixes, but if you don't already, that's okay. It takes a while to really understand and memorize them all, and that's all right. I always like to think of for nano and giga as the top two, and then there's mega, and I believe it's micro. And so because it starts with an M, they're not highest because they match, if that makes sense. So it's easy to keep track of because of that. That's just me. So we have 612 grams to milligrams. And so using the same thing we did for, we have 612 grams, and we're going to put that over our 1. And because there are 1,000 milligrams in 1 gram, we will put grams on the bottom to cancel out the grams, and 1,000 milligrams here. Milli stands for 1,000, and there's 1,000 milligrams in 1 gram, so it's 10 to the negative 3. You can always use that conversion as well. For 10 to the negative 3 grams equals 1 milligram, because milligrams are tiny, and then kilograms are large, so it contains more grams there. So because we can cross out these, we will end up with milligrams. So that will be multiplying those to 612,000 milligrams. And because we started out with 612, we have 3 significant figures, and so our final answer has 3 significant figures because of all of these zeros, and because there is no decimal place. If there was a decimal place, like I did before, this would include 6 significant figures because of that. But because we don't have a decimal place, that's important. We keep it at 3, and that's what we started with. We want to add more significant figures because we're not in anything more. So let's move on to 72C. And so we have 3,779 micrograms. And we're going to convert that to grams. And so we have 3,779 micrograms over 1, and that's what we want to start with. And we want to put that into a gram amount, and using, oh, sorry, let me look at what you said. 72A, the milli is 10 next to, what was taken out, changed to 10. Yeah, sure. You said 72A. Let's just move this down here. Yeah, sure. Okay, so I like to think of it as when you're working with milligrams, it's a smaller unit than grams, if that makes sense. So you're going to have more of the smaller stuff of the regular stuff. So because milli stands for 10 to the negative 3, that's what a gram is. So 10 to the negative 3 grams for 1 milligram. Because this 10 to the negative 3 here, it stands for milli. So that's why we use that conversion. And sometimes it's easier to start with the larger version. So if we have multiply both of these by 1,000, move that down. The 10 to the negative 3 times 1,000, that just equals 1 gram, right? And then 1 milligram times 1,000 is 1,000 milligrams. It's whatever way you want to use it. So you can use the 10 to the negative 3 grams for 1 milligram, or you can use 1 gram for, milligram here. My bad. For 1 milligram. So these were the same. So you can use the larger or the smaller kind of ratio, but they're the same. Does that kind of explain your question? Awesome. Okay. Yeah, it's all about ratios. So it's whatever makes you more comfortable. It's the same thing with milliliters and a liter. So milli, right? It's a smaller unit, so it's going to be a smaller amount of liters to milliliters. The same thing with milligrams. And we'll have one more example of that here as well. Okay, so for C, we have 3,779 micrograms. And so we're going to transfer that to grams. So in micrograms, there are 10 to the 6th micrograms for 1 gram. And so this is similar to what I did last time. There is more of a smaller unit for the regular unit. So because microgram is really tiny, you need a lot more for the base unit of gram. So that's why 10 to the 6th micrograms for 1 gram. And micro means 10 to the 6th, or 10 to the negative 6th. And for that same ratio we did before, that's why that works out. So when you multiply these two, or you actually divide, so 3,779 divided by 10 to the 6th equals 3.779 times 10 to the 3rd grams. So because we started out with 3,779, we have 4 significant figures here. So we're going to have 4 significant figures after. And the 10 to the 3rd does not matter because of scientific notation, and it's just using to multiply whatever our base term is. Okay, now let's move on to one more example. And so this is 72D. And so we have 0.13 milliliters to liters for this example. So again, I like to start out with 0.13 milliliters over 1. And so we want to get to liters. So on the bottom here, it has to be milliliters. So we have 1,000 milliliters for every 1 liter. Or like you were talking about earlier, David, if it's the same thing to have this well. So that's what that conversion would be. It's the same thing. 1 milliliter is also equal to 10 to the negative 3 liters because you're reducing it down. But I like to use the top example. So we will use that for now. And multiplying those two will have us at this amount, 0.0013 liters. And this is still 2 significant figures, just like we started out with. Okay, now let's move on to our second to last question. This one is a very big problem. And I will go very slow about this because unit conversions, when you have a lot of different conversions, can kind of get tricky sometimes. So it's best to go slow throughout. So 84, the question is, there is an average speed a Grand Racer winner. I have no idea what this is, but that's fine. Just say there's an average speed of, I don't know, a drop of rain for easier understanding. So we have 289.8 kilometers per hour. And so why are you confused? You can let me know. Let me just finish writing this out and you can go and ask your question. You want to convert kilometers per hour to total time over total time. So average velocity is actually, it's not total time over total time, it's total distance over time. If it was time over time, those units would just cancel out and it wouldn't have any meaning, it would just be value. Is that you're confused about just what average velocity is? Then why average velocity? Final, that's to do with something else. So acceleration, we're not working with transferring velocity and acceleration here. We're just using what a velocity value is, and we want to convert it into different velocity units. So kilometers per hour, we're going to do miles per hour, meters per second, feet per second. It's always distance over time. Acceleration has to do with distance over time squared. So that is something different. We're not working with acceleration here. But if you want, I can do an example of what a unit conversion is like for acceleration. It gets more tricky because the time is squared. So you have to work with time squared conversions. But we can get on another example. Am I answering your question at all? I can talk to you after about how average acceleration can be from velocity. But of course. So we have miles per hour we want to convert it to, as well as meters per second, as well as feet per second. So we're always going to start out with the value here, and we're going to go through what that looks like with conversions to here, as well as to here, as well as to here. So let's start out with 229.8 kilometers. And because we have a per hour here in the denominator, I'm going to have to divide all of this by an hour because we have 229.8 kilometers per hour. So that'll be easier for our unit conversions for crossing things out and keeping track of where everything is going to go. So for the first one, we want kilometers 1.6. Yes, you're right. Yeah, there is 1.6 kilometers per mile. So we have 229.8 kilometers per hour. Since we want to go for the first one to miles, we want to cancel out this kilometers. So for 1.609 kilometers, you're right, Masad, that's how you pronounce your name. Sorry if I butchered it. 1.609 kilometers for every 1 mile. And so because we have kilometers on top and bottom, we can cancel this out, and we're left with miles per hour. And dividing those two. Yes, you're right. Yeah, for 1 kilometer, there's 1,000 meters. And so this answer is 142.8 miles per hour. And then, like you're saying, chat, yeah, we're going to go from meters per second. So starting over at 229.8 kilometers per hour, we want to go to meters per second. Yeah, awesome. Yeah, that's exactly. You got it. So good on you for going ahead. So we want to cancel out kilometers like we just did, and want to go to meters. So there are, for every 1 kilometer, 1,000 meters. And because we cancel out kilometers, we have meters per hour. And so like you're talking about in the chat, we're going to go from meters per second. So we want to cancel out the hour here. So for every 1 hour, you can do, like you said, for every 1 hour, there's 3,600 seconds, or you can do from hours to minutes to seconds. Oh, that's awesome. Yeah. That's super cool. Me too. I'm a super big physics, math, and chemistry nerd, so super awesome. So we're going to go to minutes first. I think sometimes it's easier to kind of wrap our head around with unit conversions when we go for slower amounts of conversions. So for every 1 hour, there is 60 minutes. And we're going to also go to seconds. So for every 1 minute, there is 60 seconds. And so what you said in the chat, basically you just multiply the 60 to combine those two. Same thing, that's 3,600, but we're going to go slower. Oh, cool, yeah, algebra and kinematics, that's super cool. So because we have canceled out the hours here and the minutes, we are left with seconds and meters. So we have meters per second, and so what this multiplies out to, let me zoom out, is 63.83 meters per second. And so because we started out with 4 significant figures, we're going to end with 4 significant figures, just as we talked about earlier. And then our last one that we want to convert to kilometers per hour to feet per second. So this one's more conversion heavy. So we're going to start out with 229.8 kilometers per hour, just as we did. And we want to, our end goal is feet. So what I didn't really go over this before, but what I really like to do is go from the base unit of whatever we have. So kilometers, that's not the base of the unit, meters is. So I always like to go from kilometers to meters, and then whatever I have as my base unit, it's easier to kind of then convert to something else. So let's do that. So in 1 kilometer, there is 1,000 meters. And so that cancels out. So now we have meters. And so in 1 meter, put it on the bottom, so we want to cancel that out. In 1 meter, there is 3.281 feet. We're not doing inches, but yeah, that would be kilometers per meter. Yeah, that would be a perfect way to go about unit conversions, yeah. But for right now, we're just doing feet per second. Okay, so we cancel out kilometers, we cancel out meters, so we're with feet. So we're done with that unit, and so we want to go from feet per second. So we still have an hour right here, so we want to cancel that out. So in 1 hour, just like we did before, there's 60 minutes, and in 1 minute, there's 60 seconds. And so we cancel out the minutes, we cancel out the hour, and we're left with feet per second. And multiplying all of that out, we have 225.8 feet per second. So that concludes that problem. It's sometimes confusing keeping track of everything, and that's why highlighting, maybe crossing out is easier, and making sure when you're crossing things out, the units that you're crossing out is from the top and the bottom, and that's how you cross out. Cancel. Okay, so that was problem 4. Let's move on to 90, and this has to do with a little bit more of unit conversions as well. Nasad, yes, I'm teaching chemistry 221 for anybody who needs a little bit of help with concepts each week and some practice problems that are relevant to what they're learning in class. So it's the general chemistry series, and this is just the first week. So this is going to be 90A that we're working from the book, and we have a mass of 4.00 centimeters cubed, of course, of sodium, and we have a density of sodium to be 0.97 grams per centimeter cubed. Okay, so what we want to do is find the mass of the sodium, and so we're going to start out with how much volume that we have. So we're given in the problem that we have 4.00 centimeters cubed, and I'm going to put it over 1, like I have done before. And so since we want to find the mass, mass over volume. Whenever I think of density, I've never gotten that out of my head that it's like this, and this kind of looks like art. Oh, sorry. Kind of cut in half, if that makes sense. That's why I always remember mass over volume, M over V. It's like a heart cut in half on the X direction. So I think that's really fun. So since we want grams, so grams is the mass in this scenario, we want to cancel out the volume unit, and so that's the centimeters cubed. So we'll put the centimeters on the bottom, and so using our density from the problem, we have centimeters cubed on the bottom, and we have 0.97 grams for every centimeters cubed. And so because we put the centimeters cubed on the numerator and the denominator, we can cancel those two out, and we're left with grams, and then we specify what the question is asking of us to find the mass, which is the grams. So 4 times 0.97 is 3.9 grams of sodium. And because we started with 2 different values that we multiplied, as I went over earlier, we had a 4.00 and a 0.97, and because we multiplied them, we used the least amount of significant figures that we used in the problem. So this one has 3, and this one that has 2. And so because that one has 2, then we only round to 2 significant figures for the final answer. So that would be our answer. And for our last question today, we're going to be going over 90B. And we have a mass similar to the last one, a mass of 125 milliliters of gaseous chlorine. And they don't say this in the problem, but chlorine, gaseous chlorine, it can look like this. And the density of gaseous chlorine density is 3.16 grams per liter. Okay, and so since we have 125 milliliters, we'll start with that. And keep in mind that is 366. And so we have 125 milliliters, and I'm going to put a 1 below it. And so since the density that we're working with is liters, and we start with milliliters, we're going to make a unit conversion from milliliters to liters first. And so there's 1,000 milliliters in 1 liter. And so now we're in liters. And so now we can use the density to find the mass in grams. So we'll put liters on the bottom since we want to cancel that out, like so. And we have 3.16 grams here. And now, since all of our volumes have canceled out, we have mass left over. So meters cubed, let's see, wonder. I believe so. 1 liter equals 1 kilogram. I think you're right. I know that 1 milliliter equals 1 grams cubed. So I believe you're right in your conversions. Yeah, because 1 gram equals a cube of centimeters. But for now, we don't need to use conversions for this problem. But yeah, you're right. So we have 125 divided by 1,000 multiplied by 3.16 in that order, and we'll come to 0.395 grams of gaseous chlorine. So that's how we did the unit conversion for this, and we found the mass by using the density. It's always important to line up whatever you're crossing out and try to figure out what your end goal is and how the quickest way going about that will be. And so since we start with 3 significant figures, we have 3 significant figures in the final answer, and so that's 0.395. Yeah, of course not. And so that's the answer for this problem. So those are all the problems I have for you guys on unit conversions and significant figures. If you have more questions, tutor in the Learning Center. I tutor, so my position is to tutor here, but I'd be happy to help you at the Learning Center during the stream. I might be going over there to do this live stream, so I can sit next to you and you kind of can see what I'm doing, if that works too. I'd be happy to help outside of it. But yeah, that concludes everything for today. Do you guys have any more questions? Oh yes, the next class, it's every single Friday at 12 to 1ish. That's the hours that I'm streaming on. But if that's all for today, I'll end the stream. Thank you so much for tuning in. I hope I made it easier to understand what significant figures mean and how to keep track of all of those values as well as unit conversions. So bye guys.